Okay, in today's lesson we'll be looking at mass spectrometer, with our learning objectives of being able to identify parts of a mass spectrometer, identify the changes made to the sample at different stages. So we input a sample and I want to look at what happens at each stage, and also explain how mass spectrometry works. So we've got two pictures here. We've got a picture on the left which actually shows you what a real mass spectrometer looks like, and on the right we've got a diagram to help us explain how it works. It's the mass spectrometry itself is used to determine the relative atomic masses of different samples. So you might put an element in, and you might want to know in that element what isotopes we've got. So remember, isotopes have different masses. So we put that element into the mass spectrometer. It will show you all the different isotopes. You can also do this for molecules. You don't need to go into this in too much detail, but AQA say you do need to know that this can also be used to identify molecules as well. So we're going to break the stages down, or what happens in each part. So in each slide we've got a broken down image of the mass spectrometer. So we're looking at this part to start with, and above you can see the image, the cut out image. Now a few key points you've got to know to start with. Firstly, this black arrow shows where we put the sample in. The sample goes in here. Now the sample can either be a gas or a volatile liquid. If it is a solid, it needs to be vaporized first, so then it turns into a vapor and can pass through the mass spectrometer. Now some other key parts to look at are here. We've got the electron gun. And also we'll look at this section in a second. Okay. The electron gun can also be called maybe heated cathode. That's the main part of the electron gun. Okay. So the first stage we're going to look at is actually before we put anything in. As you can see here, we've got the electron gun. Our sample is going to go in here, and this is, like I say, before anything's happened. So that's what it looks like to start with. Then we're going to switch the electron gun on. What the electron gun is going to do is send electrons from the heated cathode or the electron gun and send them across. So you can see two electrons in the middle there. They've come from here and they're going to end up over here. So that electron gun is firing electrons across the mass spectrometer. So now in this example, we've got our sample in there. Okay? So our sample is represented by those purple dots. So the sample has been put in. The sample is then going to be passed through the mass spectrometer. We've seen here, so it's going to start to pass through. As you can still see, you've got these electrons still passing across. Our sample hasn't gone past those yet. We're going to have multiple electrons, so the electrons are going to keep firing. It's not the same electrons going by, they're going to keep firing across the path of the sample. Now, as those our sample passes by that electron gun and the electrons path, what happens is the electrons hit our sample and hit electrons off. So you can see we started with 2 electrons firing across, and each of those electrons is not one electron off either of our 2 samples, and we'll say they're atoms for this part. Okay, and the atoms, the key thing to now look is you can see that the atoms are now charged. They've lost the electrons. Those electrons are just going to go over here with all the others, and they're now charged. So that's the first stage, the ionization stage of the mass spectrometer. So that's where you're putting your sample in and it becomes charged. So if we look at our diagram, it's going across here. As it crosses that path of the electrons, the sample loses 1 electron from each atom, and each atom becomes charged. So that's the first stage. The second stage is acceleration. So now we're looking at the second part, so around here, of our mass spectrometer. And what we've got is a negatively charged plate where the ions, remember they've now formed ions, positive ions, are going to pass through. So, use this diagram to show. So it's going to do two things. First thing, it's going to make them into a narrow stream. So any ions that hit here are not going to pass. They're going to go straight through here. Now, as they pass through these negatively charged plates, they're accelerated. Okay, so there's obviously that repulsion, that attraction between the positive and the negatively charged plates, and that draws them through, and they become accelerated. They go at a faster speed now through the mass spectrometer. That's the acceleration phase. The negatively charged plates increase the speed or accelerate the charged positive ions as they pass by the charged plates. One other thing that I just is worth mentioning is the acceleration, or the amount they accelerate, is dependent on their mass. So if you've got a really heavy positively charged ion, then it won't go as fast or won't be accelerated as much as if you've got a lighter ion passing through there. So now you've got the particles accelerated, and then they're into a narrow beam. Another thing to note, going back to the first stage, is that actually you can get ions of a positive 2 charge, so where 2 electrons are knocked off of the atom. This is unlikely. I think it only happens 5% of the time, but normally we only get a positive 1 charge, but we can have a positive 2 charge also. So going to our third stage, deflection. Okay, in this stage, the ions are going to pass through an arc of approximately 90 degrees. Okay. So you can see here our ions passing down this way, being accelerated by the negatively charged electric plates. Now, they're going to pass into this magnetic field. This is going to cause deflection. Now, the extent of the deflection is dependent on a few variables. Firstly, what we want it to do, so is deflect a perfect arc down this way towards the detector. Now, there are some things we have to consider. The first thing is the mass of the atom. The heavier the atom, or heavier the sample, or the ion, sorry, the less it will be deflected. So if this line that we've just drawn now represents a maybe medium-sized ion, if you had a heavier ion, the magnetic field would have less of an effect on it, so it wouldn't draw it round that arc. It might hit here. Again, if you had a lighter ion, the magnetic field might have a much greater effect on it and draw it on this side. And this is how we get the separation of the atoms. If we've got more than one type of atom that we put in, or now they're ions, this is how we separate them. So the first thing that is affected is mass. The heavier it is, the less it's deflected. The lighter it is, the more it's deflected. The second thing is the charge. If you remember, we can either normally get one positive charge and sometimes positive 2 charge. Now, a positive 2 charge is going to be deflected twice as much as a positive 1 charge. Okay, so the charge, the magnetic field has a stronger effect on a higher charge. That's the second thing. And the third thing that's going to affect the arc which those ions come round, is the strength of the magnetic field. Okay, so within a mass spectrometer, the magnetic field has a variable strength. It can be increased or decreased, and this will affect what ions pass here. So if you had, let's look at this one again, the ion that was too heavy or was heavier and therefore didn't deflect enough, if we increase the magnetic field, it would cause that ion would reach our detector because it's having more effect, and the magnetic field is having more effect on the deflection of that heavier ion. So we're going to look in more detail about how we can change these things. But that's the key things you need to be looking at when you're looking at deflection. The last thing now is the detection. So in detection, we look at the ions that actually reach the detector. And this is only a small detector. The detector isn't around these areas, okay? It's not here. The only area it is at the bottom here. That's our detector. And only the ions that reach that detector will be detected. Like I was saying, we have those three variables: the mass, the charge, and the magnetic field strength. So the only one we're going to look at really now is the mass. So we've put in our sample, and within that sample, if they're different, there's different parts of that sample, they're going to have different masses. So if we look at isotopes, they're going to have different masses. So we've got three lines here. We're going to represent three different atoms. Atom A is our lightest. Atom B is the middle weight, middle mass, sorry, and atom C was our heaviest. Okay, we've also got three beams there, you can see. So the three colours, we've got purple, blue, and green. Now, for atom A, it's the lightest atom, or we actually should say ion, okay? So because they're ions now, so it's the lightest ion. Now, the magnetic field is going to have the strongest effect on this ion, and therefore it will deflect it the most. So, the lightest one, atom A, is going to be represented by this green one. Okay, because it's the lightest, it's being deflected a lot. The magnetic field is drawing it to the side, and it's going to hit the side before it reaches the detector. Now, atom B is the middle one. Okay, so it's got the middle mass. The magnetic field is going to have the perfect strength of it, and it's going to hit the detector. There. And atom C is the heaviest. The magnetic field will have less effect on it, therefore it won't deflect it enough. It'll hit the side over there. So we've detected one atom there. Now, that's only showing us one thing within our sample. So what we do, we change the magnetic field. So for this example, if we were to increase the magnetic field strength to make it stronger, then what would happen then is our heaviest ion, so atom ion C, would be deflected more and reach the detector. There's one that reached the detector originally, but also hit the side. So now we're detecting another ion, another part of our sample. Again, I'm just going to go over these lines so it's a bit easier to see. Again, so we've detected two of our three now. So we had our middle one to start with. We increased the magnetic field to get the heavier one. Now what we can do is decrease the magnetic field. So if we decrease the magnetic field, it's going to deflect the lighter one less, and that will reach our mass spectrometer detector. The other two will just hit the wall because they're heavier. So that's the way we detect different ions. We change the magnetic field strength, and therefore different ions will reach the detector. If we go from a whole range of different magnetic field strengths, then we should detect each ion separately. Now, that's all the stages within the mass spectrometer. Now we look at what we actually get at the end. But first we're going to try and label this. So in your book you should have something similar to this. It looks slightly different. You need to label all the key parts. So pause it here and just label those parts. You can also refer to the textbook for help, but try and do it on your own. I'm just going to quickly go through the stages IADD. So you've got ionization, acceleration, deflection, and detection. Okay, so going through this all in one go. Our sample is input. It is passed through or passed by the electron gun. Now the electrons being fired across knock electrons off of our sample and then form ions. They form positive 1 ions normally, but also we can form positive 2 ions as well, but less likely. That's ionization. The next stage is acceleration. The new ions pass through the negatively charged plates, and this causes them to accelerate. The extent of the acceleration is based on their mass. So heavier ions are going to be accelerated less, and lighter ions are going to be accelerated more. This acceleration stage also makes them into a narrow beam. So any that aren't in a beam are going to just hit the plates here and here and cause some rest to go into a narrow beam. So that's acceleration. Then we have deflection. Deflection is caused by this magnetic field, and the magnetic field can go either way. In this example, it's showing that it's going from the bottom to the top. So in deflection, if we've got some atoms that are too heavy, they're going to be deflected against the wall here. They're not going to be pulled across enough or deflected enough. If we've got ions that are too light, the magnetic field is going to deflect them too much and they're not going to reach the detector. And we're going to have ions in the middle that hit the detector. We can then change which ions hit the detector, so that's deflection, change the ions that hit the detector by changing the strength of the magnetic field. So what we're going to look at now is what actually comes out. So when it hits the detector, we've done the mass spectrometry of our sample. We've changed through that period of time, through that mass spectrometry, we've changed magnetic field, and we've found out we've got this mass spectrum. And this is mass spectrum of neon. So originally we would have put neon into our mass spectrum, and this actually shows we've got 2 isotopes of neon. Okay, we've got this one here, that's around 20, and we've also got this one here, which is around about 22. Okay? So we've got 2 isotopes of neon. We've got neon 20 and neon 22. So there are 2 isotopes. So that shows you the 2 isotopes we've got. So along the bottom, it's the mass to charge ratio. Okay, don't worry about the charge ratio at the moment. I'm just going to look at the mass. On the side, it shows you the relative abundance. So on this example, we've got 90% of the neon we put into the sample is neon 20, and 10% of it is neon 22. Okay, so we'll put this to the side. That's what it shows us. Okay, so it shows us the isotopes we've got there, or the different ions within our sample. It also shows us the abundance of that ion within our sample. Something else that can come up is you can get doubly charged ion peaks. Okay, so this is an example of chlorine. Okay, so we've got the 2 isotopes of chlorine. We've got chlorine 35, which is here, and chlorine 37, which is here. Okay, so there are actually only 2 isotopes of chlorine within this sample, the 35 and the 37. We're also seeing 2 peaks here. The reason we see 2 peaks here is because these have been doubly charged. So as they pass through the ionization stage of the mass spectrometry, where we're firing electrons at them, what's happened is they've actually formed positive 2 ions, okay? And when we form positive 2 ions, we get a mass spectrum reading of about half. So this peak here, shown here, the doubly charged chlorine 35, and this peak here is shown here, the doubly charged peak of 37, chlorine 37, and you'll get this double peak. They're less because obviously there's less doubly charged ions, that's about 5%. That's the peak you might see on some mass spectra. Now going back to our mass spectra of neon, from this information we actually work out the relative atomic mass of neon. Okay, so we know we've got, if we had 100 neons, so this is instead of using percentage, if we had 100 neons, 90 of those neons would be neon 22. And if we had, again, 100 neons, 10 of those would be neon 22. So we're going to try and work out the relative atomic mass of neon. So what we do is we take our percentage or our number, if there was 100, and times it by the atomic mass, the relative atomic mass of that isotope. So 90 times 20, and 10 times 22. We add those together and divide by 100 to get our average, which equals 20.2. So that's the relative atomic mass of neon based upon its 2 isotopes. So as you can see, the relative atomic mass, firstly based on the isotopes that we've got, so we've got neon 20 and neon 22, and the relative abundance of those isotopes. So we've got more 20 than we've got 22, so it's closer to 20 for our relative atomic mass. Something else you need to be able to do is look at the uses of this mass spectrometry. So you've got the use of them in forensics, so you can identify different samples, so in urine or blood. You can also use it for carbon dating. So with carbon, we've got different isotopes of carbon, and they've been present at different points in time, or different percentages at different points in time. So if we look at fossils, see what type of isotope of carbon we've got in there, and the abundance of that isotope, we can start to date it. And also in space, we use mass spectrometry. So we'll send satellites into space, have a mass spectrometer on there, and look at space dust or dust around different planets, or just samples of different things in space. And using mass spectrometer, we can identify those molecules or atoms that are there. Okay, now I just want to look at what AQA actually so you need to know. So you need to understand the principles of simple mass spectrometer, limited to ionization, acceleration, deflection, and detection. So we did that at the start. Now, the mass spectrometry gives accurate information about relative isotopic masses and also about the relative abundances of isotopes. So that's when we looked at the mass spectrum, and we saw the different parts there. Be able to interpret simple mass spectra of elements and calculate the relative atomic masses from isotopic abundance limited to mononuclear ions. Okay, so that's what we did for neon. Okay, it says mononuclear, so you're not looking at more than one. So that was for what we did for chlorine. You've got other examples in your book that you'll be trying to do. And second to last one, know the mass spectrometer can be used to identify elements as used, for example, in planetary space probes. So have a look at different things where mass spectrometry can be used. And know that mass spectrometry can be used to determine relative molecular masses. Like I said, you go into this more in detail, but you can also use it to determine molecules and the relative molecular masses of molecules. That's all you need to know about it, though.